And our last speaker for this session will be Nichol, and we'll be talking about supernova 15BN. So looking at a new benchmark data set for superluminous supernovae.
Okay, hi everyone. First of all, I'd like to thank the conference organizers for a really special week here. It's been great both to learn about the history and the culture of the island, but also for us younger astronomers, it's been nice to find out how difficult it was to do science before the internet. Okay, so I'm going to talk about the superluminous supernova 2015BN. First of all, a quick overview of what a superluminous supernova is. So some people have kind of mentioned these things before, but to be specific, so these are objects with absolute peak magnitude brighter than -21. So this makes them 10 or 100 times brighter than normal core cloud supernova. And this time luminosity goes on for many weeks or even months, so the total radiated energy is orders of magnitude higher than other supernovae that we see. But they're also extremely rare, making up about 1 in 10 to the 4 core cloud supernovae. So I'm specifically interested in the type 1 or hydrogen per superluminous supernovae. So there's some spectra here at the top plot. And these things have extremely blue spectral energy distributions, and at maximum light, they're dominated by broad oxygen-2 absorptions. But despite most of them having quite similar spectra, there's a whole diversity of light curves that we see with some fast and slow declining events. So the key question really is what actually powers these luminous, long-lasting light curves. We don't really have a consensus on that yet. Hopefully this new supernova will help to clarify that. So, okay, so 2015BN was discovered by Pan-STARRS and Catalina and also recovered in ASASA data. So we got really well sampled early time data. It was classified by PESTO as a young object at a relatively low redshift. 0.1 is roughly the closest where we find these things. And these things are all in faint galaxies, but this one was a particularly faint one for such a low redshift event. So it's really ideal to have a dedicated follow-up campaign. So let's look at the data. Well, I've found several papers on this for myself and others, but here's the data from the first paper. So really this is unprecedented for a superluminous supernova. We've got there's light curves sampled every couple of days from Swift bands all the way through to near infrared. We've got about 30 optical spectra. So we really have a complete picture of the photometric and the spectroscopic properties here. So I'd really like to advertise if anyone wants to model a superluminous supernova, this is your data set. So we'll look at some results from this analysis. If we compare the light curves to some other superluminous supernovae, we can see this is one of these broad events. Very long-lasting light curve. Seems to be a slightly rarer subclass. It's not yet clear whether it's a continuum of events between the fast and slow ones, or if they're two separate classes. But this is really the first time we've got a clear picture of these kind of bumps and wiggles in the light curve. So despite the very slow overall photometric evolution, there seems to be some kind of variability on kind of 30 or 50-day timescales. And these are particularly pronounced in the U-band and the Swift filters. So we're not really sure what powers this short-term variability. It's been seen slightly in some other objects, but not with this kind of sampling. But it could be related to some kind of inhomogeneous density profile around the star, or perhaps some kind of breakout of UV ionization. It depends on what your preferred model is for the overall luminosity. The spectra, the spectroscopic evolution is similar to other objects, particularly slow declining things like 2007 BI, PTF12 DAM. But again, we've got denser sampling and really high signal noise. So here's a compilation of some of the nicest spectra. We can zoom in and analyze these in some more detail. We've really got a nice picture of the individual line evolution. So as it turns out, the spectra, we haven't really seen this before because of the sort of random time sampling of other events, but it seems to separate very cleanly into two phases. The spectra before maximum, these are continuum subtracted, these are actually very blue, are dominated by oxygen 2, iron 3, and after maximum there seems to be a quick transition. The temperature drops and we see lower ionization lines of calcium 2, iron 2, oxygen 1. We can actually zoom in and look for weak lines of other things. For example, there's some hint there could be some H alpha in here. It's not totally clear. It will be the first sign of hydrogen in one of these objects if it was confirmed. We need to do some spectroscopic modeling to check that out. But once again, this is really the first chance we've had to look for these things. We can build a really nice bolometric light curve because of our coverage from UV through the near infrared. We've got K-corrections for all these spectra. And you can see these undulations before, maximum, and after really clearly in bolometric space. And these also seem to coincide with changes in the temperature. There's some kind of temperature plateau here where we get this bump. The bump also seems to coincide when the photosphere starts to recede. So these are all important clues for figuring out what this power source is. We've also got radio data of this event. We searched with the VLA for associated GRB afterglow. You might ask, why do we look for GRB? Well, there's been several arguments that superluminous, supernovae, and gamma ray bursts are related. For example, they appear in similar locations within host galaxies, and in fact similar types of host galaxies, these metal per dwarf galaxies. And there's one very bright supernova, not quite superluminous, but reached about -20, it's SM 2011 KL. And this was associated with an ultra-long gamma ray burst. So we searched at 8 and 22 gigahertz, and we got the first kind of constraining limit on the radio emission from superluminous supernova. Typically, these are too high redshift for the radio observations to be particularly constraining. We put a limit of about 50 microjanskis on the emission here. And you can see, in comparison with sort of typical GRB afterglow models, for a range of viewing angles, or jet angles, there cannot be a healthy GRB associated with 2015 BN. So that's an important result for this GRB connection. We can't rule out low luminosity GRBs. If it had been a 98 BW, we would not have seen radio with this phase. So for the next nearby superluminous supernova, we want to get radio data around maximum light. The radio is also useful for checking the CSM density profile. And actually, this radio limit rules out a range of interaction part models. So these are just some predicted radio light curves for a simple radio interaction model. And the only way to, I guess, have an interaction powered optical light curve without this radio emission is to either have an extremely dense CSM, mass loss rate more than 100th of the solar mass per year, or some kind of truncated mass loss where the shock actually breaks out around maximum light. So this is good. It's one of the first kind of tests outside the optical for what models could power the very bright emission. Okay, so this is a second paper on the subject, and this came out a couple of days ago. You can imagine the fun that I had trying to upload this to AstroPH. And obviously no one's going to read it until next week. But we now get data for this that goes out to about 400 days after maximum light. And again, we've got from the U-band through the near infrared, so a really reliable bolometric light curve extending out, I guess probably the furthest we've ever followed one of these events now. And previously, the decline had seemed roughly compatible with cobalt decay, but our new data shows that it's actually significantly steeper. So this raises questions for any kind of Nichol-powered model to explain these things. The broad light curve suggests a large ejected mass, which would imply efficient trapping of the Nichol decay, but yeah, we see the light curve decay significantly faster than that. I think the most interesting result so far from this subject actually is the nebular spectrum. So for the first time, we've got really nice spectra probing the evolution from the photospheric phase, so these are spectra I showed earlier, all the way through to 400 days when the spectrum is almost completely nebular. And we can see these really strong oxygen-1 forbidden lines, some calcium lines, a little bit of iron, magnesium popping out here. And quite amazingly, it actually looks almost identical to hypernovae such as 98 BW, 97 DQ, 2012 AU. So these are all supernovae that had very large kinetic energies, around 10 to 52 Earth. And 98 BW, of course, was linked with an observed gamma ray burst. So I think the spectroscopic similarity here in the nebular phase, when we're really probing all the way through the ejecta and seeing what these things are made of, it's quite striking. It looks so much like a GRB supernova. So this really confirms the GRB SLSN connection that people have been talking about from host galaxy locations and other evidence. I should also point out that Anders Jerstrand in Queen's Belfast has a nebular spectrum paper that came out on the same day, so you should check that out also. So from these oxygen lines, we can make a few estimates about the intrinsic properties of this object. From the line ratios in the oxygen, we can derive a temperature of about 5,000 Kelvin. and that then gives us an oxygen mass. So to get this really strong oxygen 1 line, we need about 9 solar masses of oxygen, which implies sort of 15 or 20 solar masses total ejecta. So this is really quite a massive event. And from the line widths, combined with these mass estimates, it seems like a large kinetic energy is required, probably too high for a neutrino-powered explosion, which also ties in with the spectroscopic similarity to the hypernovae. We've got this very interesting oxygen 17774 permitted line, which seems to be much lower velocity than the other strong lines in the spectrum. So this is a recombination line. So it seems that somewhere deep in the ejecta at lower velocity, we've got this ionized shell, which is not seen in normal supernovae 1bc. So this could be a potential signature of an engine model that is sweeping up and ionizing its inner material. We also see some other high ionization lines of oxygen 3, which is something people have been looking at recently in superluminous supernovae. Okay, so I said at the start that the main question is to pin down the power source of these things. So the 3 main theories, large nickel mass as I mentioned, but we've got a decline much faster than cobalt. Interaction with massive CSM, but we see no narrow lines in the spectrum in any phase. And we've got some radioluminescent that roll out specific CSM interaction models. And the final and most popular model for these things is a central engine, such as magnetar spin down. I think the similarity to GRB supernovae is a really strong argument in favor of a central engine kind of model. You need something to give it a high kinetic energy, so there's already probably an engine in there, and it then seems like that's a natural candidate to potentially explain the optical luminosity. So as is the norm in superluminous supernova papers, we fitted our light curve with a magnetar spin down model. And we can fit it pretty well over a very long baseline in time and for sort of plausible parameters. Interestingly, the inferred magnetic field and spin period are too low, well the B field's too low, to expect a gamma ray burst based on some analysis Brian Metzger did. So it's quite consistent, even though we form some kind of engine. The fact that we don't see a radio after below the GRB is actually consistent with our derived light curve parameters. There is some discrepancy in the wait time light curve. I think this is consistent with the optically thin spectrum we see at this phase. This model is assuming an optically thick photosphere. So the difference in wait times when the ejecta are optically thin, just from the data and the model, it's being suggested that X-ray emission directly from the engine could leak out at late times and actually be observable. And that really will be the smoking gun for these central engine magnetar models. So we are currently conducting an X-ray search for this X-ray emission at late phases. We've got some moderately constraining limits, but we're going to keep integrating for a little bit longer, and hopefully we will have a conclusive answer to that. Okay, so I'm on the time, so to finish up. 2015BN is certainly one of the closest and best observed superluminous supernova to date, with panchromatic data all the way through UV, optical, radio, even some X-ray. I think a self-consistent picture is emerging for these objects, with the light curve and the spectrum suggest a very large ejected mass and a large explosion energy. And the spectroscopic similarity to GRB supernovae, to me, certainly argues for the central engine as the power source. So I really encourage anyone who's interested in modeling these objects to grab this data. It's on James's Open Supernova Catalog. And I think that we can learn a lot from these individual objects still. Even though superluminous supernovae are becoming kind of more common and one object is less interesting, this kind of detailed follow-up can still teach us a lot. So I do encourage people to get lots of data on these things. Thank you very much.
Questions?
For the late time light curve, so past 300 days, have you considered dust production? Do you have any near-infrared photometry around the same time?
We do have some near-infrared photometry around the time that it develops these nebular features, but there's no kind of clear access or anything. It looks pretty consistent with the decline that we saw before. I'm not sure if we expect these to produce dust at this phase, because they're still quite hot actually compared to other supernovae at similar phases.
Any other questions? If not, let's thank all of our speakers from this session.